Well, it is 11, so we can get started. As I've mentioned to most of you who are in here, there's a chat function, so you can go in and type in the chat and let us know what questions you have as we go along. We'll try to make this as interactive as possible. Today we're going to be talking about introduction to HP Multi-Jet Fusion 3D printing. And our presenter today is Andrew Roderick. He is our lead applications and sales engineer for our additive group. He's been with Extol for 7 years.
7 years.
And he knows a lot about additive. He was exploring it long before we really became this additive, had an additive group. So I think that's all I needed to cover. Like I said, if you have questions in the chat, we'll try to get those as we go along. And then, of course, we'll have a time at the end for questions. So without further ado, Andrew, take it away.
Thanks, Jason. Welcome, everyone. We're going to jump right in as we've got a lot to cover today. So why 3D printing with MJF? When you look at the life cycle of a product, there are three main phases. There's the development phase, the manufacturing phase, and the service phase. HP brings new innovation to plastic product development and manufacturing. Today, we're going to look at how MJF improves functional prototyping, accelerating development, low to mid-volume production, avoids tooling costs, making the previously unmakeable a reality, design freedom and mass customization, jigs and fixtures, and tools for manufacturing, design flexibility and speed of manufacturing. We're going to start with a short video walking through the multi-jet fusion process.
HP Multi-Jet Fusion is a powder-based 3D printing process unlocking new efficiencies geared towards enabling production. Let's take a closer look at the printing process from start to finish. The process starts by evaluating each part and selecting the optimal print orientation. The parts are then placed in the build envelope. Special care is made to balance height and pack density while avoiding sudden changes in printed surface area. Parts are nested in 3D space within the print envelope, which is approximately 15 by 11 by 15 inches. Once the build is packed, it is sent to the printer. The build unit is inserted into the processing station to be filled with powder. The station automatically fills the build unit with the desired ratio of recycled and new material. Typically, the mixed ratio is 80% recycled and 20% new. The multi-jet fusion printing process uses the highest percentage of recycled material of any 3D printing process. Once filled, the build unit is inserted into the printer and the printing process is initiated. The parts are grown layer by layer, 80 microns at a time. There are 4 steps to the HP Multi-Jet Fusion printing process. First, powder is spread across the build area. Next, fusing and detailing agents are jetted onto the powder. These aren't binders, rather, they respond to IR energy. The fusing agent absorbs IR energy and causes the powder to get hot, while the detailing agent evaporates, causing the powder to cool. This causes a sharp temperature transition, which results in a fused part with distinct, precise edges. Multi-jet fusion parts are stronger than those printed with SLS and other technologies due to greater energy exposure. On each pass, energy is absorbed multiple layers deep, creating strength in every direction. Once the printing is complete, the build unit is removed and the cooling process begins. Builds can be naturally cooled or fast cooled in the processing station. A full build naturally cools in about 24 hours and then is ready for unpacking. First, the build unit is inserted into the processing station and the archaeological dig begins. Unfused powder is vacuumed away and reclaimed for future builds. Parts are extracted and excess powder is removed. The final step is media blasting to strip the remaining unfused powder. Depending on part size and geometry, this can be automated or done by hand. The parts get a final blow-off and are ready to be used for functional prototypes, tooling, or production applications.
Excellent. So with that video being the basis of the process, I want to take a look at a couple subsystems of the printer that are unique to MJF. The upper bank of lamps control the bed temperature with feedback from the thermal camera you see in the center. The print carriage houses the print heads, spanning the entire printable area with the fusing lamps on the leading and trailing edge melting the plastic. So all types of 3D printing have time and place for certain applications. This chart shows the generalities of how other technologies compare to MJF. We're going to highlight a couple key aspects. So SLS is similar to MJF in that it is a powder-based technology, but as mentioned in the video, MJF has superior mechanical properties due to how the energy is applied. MJF has a great dimensional resolution, but SLA will provide more detail with smoother surfaces, but the downside is brittleness. You can look at those parts and they'll break. MJF is an area-based technology where increasing the amount of parts per layer does not affect print time, unlike point-based technologies like SLS or FDM or SLA, where either an extruder or a laser is tracing each individual part. MJF's Z-strength and great mechanical performance unlock functional end-use assemblies. Extol offers 3 different materials: polypropylene, PA12, and TPU. Polypropylene is a newer material for which we were the alpha development partner. Being able to weld multi-jet fusion polypro printed parts to a wide range of polypropylene or TPO family of injection molded parts unlocks more functional prototyping opportunities. PA12 is a strong rigid material with high dimensional accuracy, and TPU is a flexible elastomer that is great for soft touch and non-marking applications. There's other less common MJF materials that are on the market: PA11 for flexibility, PA12 glass bead for stiffness, and TPA is another elastomer material. We find that most of these functional characteristics can be achieved with our material set and design. So I'd like to point out a couple often overlooked properties of MJF parts. Non-porous, so they can hold liquid and air right out of the printer. And then they're thermoplastic, so they can be remelted or welded with a molecular bond to compatible thermoplastics. These 2 characteristics are key in manufacturing plastic products and important if we want to use 3D printed parts for functional end-use assemblies. Many other 3D printing processes don't have these properties, so MJF is unique in that regard. When we look at applications, many of them require doing something to the part after printing to achieve a full solution. Some finishing processes include AMT vapor smoothing. So that's a chemical smoothing process to seal the outermost surface and smooth the part. It also enhances some mechanical properties. Extol offers parts to be dyed or painted, as well as flexible color coding from BASF for TPU. Often parts are too large for the build envelope, which is 15 by 11 by 15 inches, and need to be split and joined. We help our customers split large parts every day, so don't let size disqualify multi-jet fusion. The last one that I want to touch on is we also provide welding and assembly for parts that require a strong bond or to prove out a manufacturing process. So let's take a look at an example of functional prototyping and how MJF accelerates that development. We see a lot of fluid reservoir applications for functional prototyping like this from our customers. When I say functional, I'm talking that these parts will go on vehicles. Traditionally, our customers would commission a prototype tool from a prototype shop, and then they would injection mold prototype parts, and that could take anywhere from 7 to 12 weeks. And then we would, excuse me, then we would complete the hot plate welding at Extol on our hot plate welding machine in our process development center. And that can be a day or two. Some initial validation of the weld at Extol, and then we would ship the customer to complete cycle testing or other validation testing. So the time to first part would be 7+ weeks. With the additive solution, we're able to print multi-jet fusion parts at Extol, weld, and ship parts in days instead of weeks. This hot plate welding example is a polypropylene fluid reservoir as shown in the multi-jet fusion process video at the beginning of the webinar. It was welded on Extol's rapid conductor, which is a hot plate welder, and the weld joint is airtight, so it's a hermetic seal. And there's also parent material strength in burst testing, so that means it cracks away from the weld. This is what we like to see in both molded and printed parts. So here's an example of the hot plate welding process in action. So the 3D printed parts loaded into a fixture. The horizontal heat plate is about 500 degrees Fahrenheit, and the weld ribs on the part touch that heat plate to melt. The heat plate is then retracted. You can see the black melted weld ribs, and then the parts are held together under force until the process or the material resolidifies. This is a strong weld that we use every day with molded parts, and it's really cool to be able to use multi-jet fusion printed parts to bring functional prototypes to reality, combining additive manufacturing and traditional manufacturing welding technology. When comparing injection molded and multi-jet fusion results, we find that the burst strength is reduced slightly due to the different manufacturing process. The multi-jet fusion parts still met our customers' requirements. However, we could alter the part design to increase strength if necessary. And then, of course, the lead time, as mentioned before, goes from weeks to days, and everything else is comparable. Now let's look at low to mid-volume production. This example is a COVID-19 respirator component. Polypropylene made this application possible due to PA12 being too brittle for the thin Christmas tree clips. They needed more ductility. From the initial conversations with our customer, with a few iterations in design, to the start of production was only 1 week. There were a lot of unknowns with quantity and design, length of program, so our customer wanted to avoid tooling risks. We produced 28,000 pieces in 3 weeks with a total project life cycle of 4 weeks. And you can see the build box in the lower right-hand corner has about 1,700 parts shown there. Another part of the manufacturing with MJF is making parts that are not possible with other manufacturing technologies, making the previously unmakeable a reality. This is a great example of how HP and Siemens partnered in making the previously unmakeable a reality. The first iteration of this intake started by combining parts into one assembly, reducing costs associated with molding several components. Next, by using computational fluid dynamics and the design freedom of multi-jet fusion, the geometry was optimized to improve flow. So basically, letting the computer do the work to find the optimal solution. You can see here the results from that computational fluid program, and you can see that the flow is now laminar around the corner of this 90-degree turn, and the organic shape that allows that to happen. The shape couldn't be created in any other manufacturing process. So creating a lot of process improvement and the ability to make your product better without certain restrictions that you've had in the past. So when we talk about jigs, fixtures, and tools, this spans across the whole product life cycle. And one example that we want to touch on there is soft touch tooling, which uses the BASF TPU to hold parts and prevent marking. It's often used with vapor smoothing, and it's an alternative to poured urethane. It can be applied to anything that is touching parts, so fixtures, end-of-arm tooling, shipping dunnage, etc. So now let's take a closer look at what needs to be considered when designing for multi-jet fusion. With every new technology, there needs to be a mindset shift to fully take advantage of the process. So we're going to look at 3 different points considered when designing for injection molding and what that translates to with multi-jet fusion. When we think about die draw in injection molding design, we now want to identify the build direction with multi-jet fusion. So when you look at build direction, there's different print orientations will optimize different property characteristics. So let's take a look at this part and consider our options. If the round pin features accuracy is the most critical, we would want to orient that in the XY plane. So the plane of the print heads is most accurate. If the surface finish or strength is most critical, we would orient the surface that needs to be smoothest downward in the printer, and the round pin feature now has a larger cross section being fused at once, giving it more strength in this orientation. If cost is most critical, we would want to orient it in such a way that we could fit the most parts into the printer at one time. That might mean surfaces and dimensions vary slightly from part to part because the same part is oriented in several different ways to optimize quantity being printed at once. So, currently when we think about wall thickness for injection mold design, now we want to avoid sudden changes in printable surface area. So what that looks like is the printing process is a thermodynamics problem. To have the best outcome, the energy absorbed in each layer will be consistent or gradually increase or decrease. So we want to avoid sharp corners and going from thin walls to a large flat surface like you can see in the top example there, where you're building the thin walls and then all of a sudden there's a large surface area that needs to be fused or melted together. So we can accomplish this smooth transition through design, tilting parts, or nesting several different geometries together. So you can see that the dome and corrugated design versions help reduce the fused area per layer and smooth out the transition. When we think about press size with injection molding, we now want to think about pack density for multi-jet fusion. You can think of pack density as how many parts you can fit in a build. So fitting as many parts as possible will reduce the cost per piece. We want to design for process optimization. So part nesting can be improved with design changes such as orthogonal walls, mirroring outer profiles, or introducing folding features, to name a few, to be able to get more parts into a build efficiently. A common mindset in the additive space or in 3D printing is to reduce the assembly part count by combining parts, but often we see that splitting parts gives a better result in terms of cost savings. For example, printing this first design on the left-hand side, we were only able to fit 3 at a time, which didn't hit the cost or capacity requirements for the customer. The large number of additional builds needed also meant that there weren't enough other production parts to fill the unused space, drastically increasing the cost per part. A redesigned version, split into 2 separate parts, enabled parts to be nested together more efficiently, increasing pack density and driving down costs. So now we can fit 8 per build versus 3. So I know we covered a lot today, but if you remember these 3 things, you'll avoid some common pitfalls and be able to be on a great start with designing for multi-jet fusion. The first is identifying the critical dimensions and surfaces to consider for orientation and avoid sharp transitions. So by adding as many radii as possible. We are here to help design or help you decide the best print orientation to meet your requirements. So feel free to reach out with your parts and we'll be able to review those on a case-by-case basis to help you out. The second would be hollowing out or honeycombing parts where possible, to reduce pack density and be able to fit more parts on each individual layer. So you can kind of see the honeycomb on the top of that, part in the center. And the third is splitting large parts. So in this case, or in this example, you've got a large frame, and splitting it into the 4 frame sections, we're able to reduce the height and increase the pack density, which reduces the cost of the assembly. I also wanted to give those who are unaware a quick overview of Extol. Extol is a manufacturing and technology company that improves the way plastic products are made, and we're located in Zeeland, Michigan, near the coast of Lake Michigan. We support our customers in 3 main areas: plastic assembly technology, custom automation, and engineering services, and that's where additive resides. The multi-jet fusion printing takes place in our digital development center, where we produce parts from prototyping to production. Extol's experience in plastic assembly and additive manufacturing and our innovation process provide huge value to our customers. Our ultimate goal is to progress the additive industry and help our customers fully unlock additive. We have 3 HP multi-jet fusion 5210 printers, design support, and we provide customers with functional prototypes all the way to end-use production parts. So with that, I think we're going to open up our question and answer time. I'll turn it back over to you, Jason.
Thanks, Andrew. Great job. Yes, it's time for questions. I know that we went through a lot of information pretty quickly. So you probably have some questions. Maybe you have some specific applications that you're curious about. So hit us up in the chat. And all right, we got one already. Robert, do these materials work with infrastake, hot plate welding, or our spin welder technology? I can actually even answer that one. Yes, they do. Polypropylene is great for infrastake, hot plate welding, and spin welding. Polypropylene is just generally a really easier material to work with when you're doing plastic welding and staking. For the PA12, that also works with infrastake. PA12 and hot plate welding can be tricky. It's when you melt PA12, it becomes quite sticky. But it works good with spin welding, and there's other technologies out there too, like vibration welding or ultrasonic welding, any frictional materials, laser welding. We also do that. So yeah, it works. These materials work great with that. And then TPU, it's a little bit softer material, but that's also compatible with the polypropylene. So you could take a TPU part and a polypropylene part and weld them together. So the other question that you asked is, does Extol use SolidWorks? Yes, we do. Absolutely.
Yeah, the other thing that I just mentioned too is that the PA12 is only chemically compatible to itself. So that might limit you in having to print both halves of your assembly, where polypropylene, if you already had a molded half in a polypropylene or a TPO, you could then weld that printed part to the injection molded part. And we do that frequently for staking applications where a customer is trying to prove out a design to go from a fastener to a stake, or they're changing it slightly, and we're able to print and test that out before they cut the mold.
Yeah. And I think also when we're doing that, if you have a large assembly and you're staking some smaller components on, we can print just the area where it needs to be staked.
Yep. That reduces cost and gets you, better information faster and cheaper.
Yeah. And if you need to modify the design in order to make it easier to do pull testing or something like that, we can do that as well.
Yep.
Any other questions out there? Are there post-processing options to improve surface finish on show parts?
Yeah, so with PA12 and TPU, we do have the AMT smoothing process. So it's a vapor smoothing. And basically there's vapor that condenses on the part and remelts that outer surface. So that smooths it out a little bit better there. So you can really increase the perceived value and the function of parts with that. We're unable to do that with polypropylene, but there is, it's it's in process of being in development. It's just a newer material, so they're developing that chemical to be able to smooth it.
And we've even had people like look at a vapor smooth part and not believe that it was 3D printed.
Yeah, I just had a customer that we visited the other day, and I showed him a part, and he's like, my mind is playing tricks on me, because if you dye a part black and vapor smooth it, you can really make it awesome. We've also had customers, do like a urethane primer with paint, and that it doesn't hide everything, but it does give it a good finish.
Got a couple more minutes for questions. I can see some people are typing, so we'll let those come through. If you happen to think of a question after we end this in a few minutes, that's no problem at all. You can follow up with Andrew via phone or email, or respond to the email that you get from me, and I'll make sure you get your question answered. We want to make sure that you feel like you have a good understanding of MJF, and know that you can come to us with any questions or applications specifically that you've got.
Yeah, and I would also add too that if you found this valuable and you'd like a larger group at your company to be able to experience this, we'd be happy to do a lunch and learn or a webinar specific to your company, and present to more people there. I want to go ahead and read some.
Yeah, so the next question that came in, thanks Scott. We have been getting drawings for 3D printed spare parts. If needed, what kind of turnaround are we seeing for most applications? So how quickly can we?
Sure. Yeah. So our standard lead time is 5 business days, but I've turned projects in a day for specific customer needs. It really all depends on the project specifically and where we are at with production. But 5 business days is a very, very feasible and something that you can count on. But we can go faster.
Would you say our printers are typically loaded up most of the time, or open to capacity when things come along?
Yeah, so we do have a lot of capacity with these 3 printers. It really all depends on, there's some big projects that will fill up, but it's more chunky, right?
Yeah.
So we're able to flex as needed.
Yeah. Well, with that, I think we will wrap it up. If you didn't get a chance to answer or ask your question, feel free to hit us up via email, and we'll follow up with you there.
Sounds good.
Thank you very much for joining, everybody.
Thank you, everyone. Have a great rest of your week.